Okay, let's dive right into this explainer. Today we are unpacking a really fascinating engineering detective story. So picture this, all right? You've just brought up your brand new custom core on a DE10 Nano board. It's running. The LEDs are blinking away, but something is just slightly off. You know the feeling? It's not crashing, it's not completely broken, but the timing just isn't exactly what you expect it to be.
The designers actually put it perfectly. They said, not broken, off. That was the ghost we went hunting. And I love that framing. This subtle little anomaly sparked a massive investigation into the very architecture of the core. Because listen, we aren't just looking at a simple typo in the code here. We are hunting an actual ghost in the machine's timing logic.
So our prime suspect in this whole mystery was a phenomenon the audit dubbed A2, or Prescaler jitter. And the theory makes total logical sense. Imagine a free-running counter. If it only resets at a global reset and never actually realigns when a wait period begins, well, the first timing tick after that wait could be slightly delayed depending on the phase. This would cause the high and low intervals of a simple LED blink to scatter from cycle to cycle, basically pure jitter.
Which brings us to Section 1, Layer 4, the proof cabinet.
Now, to catch this ghost, the engineers couldn't just guess or tweak things blindly. They needed a proper interrogation room. So the crucial point is that Layer 4 isn't just some basic testing suite. It's an incredibly rigorous, expected before observed verification scheme. You have to predict exactly what the waveforms, the VCD files, should look like before you ever even peek at the results. It's an honest cabinet of proof designed to record cold, hard facts. Even negative data is captured accurately here, and it completely forces the designer to face the exact reality of the hardware entirely without bias.
Armed with this Layer 4 setup, the team ran a white box simulation using Icarus Verilog. They specifically instrumented the exact mechanism A2 warned about. They checked the Prescaler's phase the instant a wait begins and measured the delay until that very first tick. They ran this exact test across 13 different wait windows to see exactly how badly this jitter was warping the timeline. So, what did they actually find?
Well, here is the shocking plot twist. When you look at the results, the phase at entry was exactly the same every single time. The first tick delay, exactly the same. The scatter was absolutely zero. The conclusion was totally undeniable. There was literally no jitter. Our prime suspect was completely innocent. The bug we expected simply did not exist at all.
Now, what's really interesting about this slide is how it mathematically explains that initial slightly off feeling. If there was zero jitter, why did this simple blink program output 25 clocks on and 35 clocks off? Let's look at how these internal state transitions map out in the command table. The NOP command that turns the LED off and the jump command that closes the loop are both foreground commands. In this specific architecture, they are prescaled. They each cost one whole prescale unit, which is 5 clocks each, and they both happen to land on the off side of the cycle. So 25 plus 5 plus 5 equals exactly 35. That asymmetry wasn't a defect at all. The core was executing the source code flawlessly.
Okay, so this totally solves the mystery of the 25 to 35 ratio. But honestly, it opens up a much deeper question. Why was there no jitter at all? Was this just a remarkably lucky blink program that happened to perfectly land on a prescale boundary? Or was there some fundamental structural reason keeping the timing so incredibly stable?
The answer is just beautiful in its simplicity. The phase is locked, tightly. It's like interlocking gears. Because every single foreground command, including the control flow, costs a whole integer number of prescaler units. Any loop you build out of these commands will have a total length that is an exact multiple of the prescaler period. Because of the structural rule, the loop re-enters every single wait state at the exact same prescaler phase, forever. The bug wasn't fixed, it was structurally impossible from the very moment the architecture was designed.
Moving on to Section 2, Practice, looking at the duty idiom steps.
You see, understanding this structural lock didn't just solve our mystery. It actually yielded some real treasure for practical, everyday application. Because you can intentionally place the cost of these foreground commands, you can completely control the waveform without adding any new PWM registers. Let's walk through the exact steps to apply these duty idioms. Step 1. Let the cost fall entirely on the off side, giving you that original 25 to 35 ratio. Step 2. Simply retag a single command so it executes while the LED is on, perfectly balancing the output to an even 30 to 30. Step 3. You can even raise a flag bit during that command to explicitly show any external logic exactly which cycle is paying the execution tax. Or, Step 4, banish the cost entirely by pushing the control flow right to the background, giving you an exact 25 to 25 timing. It's an incredibly powerful level of control, using literally just the existing opcodes.
And this brilliantly illustrates the quiet power of what the designer calls state zero. Think about it. When a free-running clock first starts up after a global reset, nobody knows what phase the world is in. That very first state is always of an indeterminate length. Instead of trying to engineer some incredibly complex workaround, the architecture uses a single NOP instruction, state zero, to just swallow that unknown first moment whole. It's exactly like planting a flag on uncertain ground, absorbing all the initial chaos so that from the second state onward, all subsequent timings are absolute, exact, and mathematically perfect.
All right, Section 3, the handshake between white box and silicon. So everything we've talked about so far relies heavily on theory and simulation. But as we all know, the ultimate test of any hardware architecture is physical reality. To prove this actually worked, the designer captured all 4 of those duty idioms live on the physical DE10 Nano board. And here is the truly exhilarating part for any engineer listening. Because the differences between those 4 waveforms exist entirely in how the instruction memory is arranged, the engineer could swap between them live. By just editing numbers directly in the in-system memory and pushing them over JTAG, they changed the physical behavior of the chip in seconds. There was no recompile, no resynthesis required, just instant, qualitatively different behaviors observed right there in physical silicon.
Let's look at this comparison to really build a complete picture. Think of it like architectural blueprints perfectly matching a constructed building. On the left, the white box simulation explains the why behind the architecture. It shows us all those internal states, the integer multiples, and the phase locking we talked about. On the right, the physical silicon proves the that. It proves that these deeply complex synchronization mechanisms and mathematical concepts actually survive the harsh transition into physical voltages and logic gates.
And the final results? Total agreement. The silicon matched the simulation not just in ratio, but absolutely clock for clock. 25 to 30, 30 to 30, 25 to 25, the real Prescaler phase was locked exactly as the simulation predicted it would be. The white box and the board literally shook hands. The investigation, our little ghost hunt, is officially closed. There was never a bug. It was a correctly functioning architecture doing exactly what it was told.
Which leaves us with a really profound realization to close on today. The designer notes that accepting this free-running Prescaler, actually committing to its structural rules, rather than trying to engineer apologies or quick fixes for it, did a lot more than just make jitter impossible. It unlocked entirely new possibilities that we haven't even fully explored yet. So I'll leave you with this final provocative thought. In your own learning or in your own hardware projects, if you stop apologizing for your constraints and instead fully commit to them, what entirely new doors might open for you? Thanks for joining me on this explainer, and keep digging into those mysteries.